Hey guys, welcome back. In this section, we're going to take a look at image classification. Here's a quick overview of what we'll do. First, we'll look at image representation. Then we'll be taking a closer look at what makes up an image, as well as the numerical and tensor representation. We'll be doing this so that we can understand how complex a challenge it would be to make use of all the features of an image when we're creating a model or during a prediction. Next, we're going to look at a mathematical operation called convolution, and what it does is it looks at the image, but in a smaller fashion. Essentially, you have windows that let you look at smaller patches of the image. Now what this will do is it'll let us extract more meaning from this section that we're looking at, and the output of the convolution operation is a feature map. Then we'll look at another mathematical operation which is called pooling. The pooling operation is applied after convolution, and this has the effect of removing the importance of the actual location of a feature in an image. Instead, it focuses on the occurrence of that feature in the image. This is called downsampling, and it happens when the pooling operation summarizes the presence of features. Now the essence of the model that we're building is to classify images, and dense layers are required for that. We've already seen dense layers in the previous sections, but we're going to revisit how dense layers come into play after convolution and pooling have been applied to our input. Finally, we'll bring everything together by training a model that makes use of both convolution and pooling. This is called a convolutional neural network. Before we get started, let's look at one possible solution to the assignment from the previous section. That was to try and train a model with fewer than 2 million parameters, but that it was able to obtain an accuracy of 85% or more. On the screen here, I've got a notebook open, and as usual, the first thing that we do is ensure that TensorFlow is installed. We'll go ahead and import TensorFlow and import Keras from TensorFlow. Next, we go ahead and make use of Fashion MNIST dataset from TensorFlow datasets, and we split this into our training and our test images, and we'll normalize those. Next on the screen, we have a simple Keras sequential model with 2 hidden layers. The dimensions of our input images are 28 by 28, and if you multiply those, you'll get 784, which we have for our hidden layers. So those are the number of neurons that we have in 2 hidden layers. Then, we finally have an output layer with 10 neurons, and we apply the softmax activation function to this. We'll go ahead and compile this model. We'll use the atom optimizer with the default learning rate, and we specify our loss as sparse categorical cross entropy, because we're dealing with images, and there are lots of places where the pixel value is 0. We specify accuracy as our metric. Then we go ahead and fit the model on our training dataset, and we train for 10 epochs. That means we go over the entire training dataset 10 times, and we can see the output of our training. We're able to get about 91% accuracy on our training, and our loss went down about 50% from the starting loss at our first epoch. Finally, we can print our model summary, and we can see the layers in our model. So first off, the image gets flattened. Then we have our first dense layer with 784 neurons, a second dense layer with 7.84 neurons as well. Then our final dense led for our output. And we can see here that the total number of parameters is about 1.2 million. You can give it a try if you haven't done that already. Try to reduce the number of neurons in the layers and see how long you need to train to arrive at a similar accuracy, or possibly even better. Now that we're done with the assignment solution, let's look at image representation. Before we get into image, which are called unstructured data, it helps to look at unstructured data, which is data that is presented in a tabular format. For example, with the classification of iris flowers. We do not use the images. Instead, we use certain features. Specifically, we use the length and width of the petals and the sepals, and this information is sufficient to help us classify these images. Now, because of the nature of the data, we're able to use logistic regression to solve this problem, and an example of the kind of data that we have is shown in the table. So you can have features. In this case, A and B, for example, the length and width of the sepal, and then you have classes. If you go ahead and plot these details on a scatter graph, you'll see something that looks like this. In this image, we've plotted 100 examples from 2 classes. Without any special highlighting, we can't tell the difference between the classes. Once we highlight the different classes, it's easy to see that these features fall into 2 different boundaries or regions. And we're able to do this because we're able to come up with a hypothesis or a function, then apply an activation, and then find the separating threshold. But consider this image. If we wanted to classify the different items on that plate, it would have an interesting problem. So where do we start? Is it enough to make use of the width of the image or the color, or some other detail? How exactly do you describe an image? The first thing to note about image classification is that all our image will need to have the same dimensions. Imagine for a second that we make use of images that are 200 pixels wide and 200 pixels high. That's a poor resolution image, to say the least. It's quite difficult nowadays to get a phone that will not give you something better than that. Typically, maybe 1,000 pixels wide and 1,000 pixels high, or even if it's 760 pixels high. That would still be almost 4 times the size in each direction. That's for the width and height. So it turns out that this is a low-resolution image. The problem is every pixel provides information. As a result, it's a feature. Now when we take 200 pixels wide and 200 pixels high, this will give us 1,000 features for a grayscale image. Now because a lot of images come in as color images, we have 3 color channels, red, green, and blue. Essentially, this 200 by 200 pixel image would have an outstanding 120,000 features. Turns out that when we want to tell the difference between 2 objects, we need more info than color and size. So, feature engineering comes in. So how exactly do we go about engineering features for an image? Over the years, different approaches have been introduced and tried out. Turns out that neural networks are good at engineering features. So every time you add a new layer, you're adding some complexity to the model, and it helps to detect features. Now consider the image above. If you're used to seeing apples, you could tell that those are clearly apples. Even without any technical training, we could tell that the 3 apples have different features. We cannot come up with one simple manual for explaining how to tell an apple. The subtleties of describing an apple are the features of the apple in an image. So let's go to our notebook, and we'll look at the numerical representation of an image. We got our notebook up, and as usual, we ensure that TensorFlow is installed. We're going to make use of a new feature called TensorFlow datasets to get a hold of a certain dataset called cats versus dogs. We go ahead and install it. Once our libraries are installed, we can go ahead and import TensorFlow as TF, import Keras from TensorFlow, and TensorFlow datasets as. TensorFlow datasets have a bunch of datasets. It's kind of like, here's the datasets, and you could see a list of the available datasets by calling tfds list builders. And what we're interested in is the second entry in the list that we have on the screen, which is cats versus dogs. Let's go ahead and create a builder, which is the first thing we need to do. And we need to specify as a string the name of the dataset we're interested in. Next, we need to call download and prepare on the builder. After a little bit of time, it would have downloaded the data that we need. One thing that we could do is call the info property on the builder, and that'll give us metadata about the dataset because we have not gone to, say, maybe, the website where the data is hosted to read up all the information. So the metadata will give us all of that. And that info property will give us something called dataset info. We could see first the name of the dataset, which is cats versus dogs. We could see the version, the description, the URL, where the actual dataset is hosted, and there's something called features. That'll give us a feature dictionary. So essentially, it tells us there's something called image. There's something called image/file name, and we have something called label. We can also see the total number of examples. We see how the data is split. In this case, cats versus dogs are not split into training and test data set. Unlike things like MNIST, we could see supervised keys, which are a tuple of image and label, and we could see any citation that comes along with the data set. Now what we could do is load the data set into a variable called train_ds. We could see the type of variable, which we've created. It's essentially an options data set. We could go ahead and call the take function. What we want to do is take one, which is one entry from that iterative, and we're interested in the first value, which we assign to example, and we could see the example is a tuple. So let's go ahead and extract the image and label from example, and we could see that the image is an eager tensor. More interesting things, image.shape tells us that this is a 3D image. We have a width and we have height. we have a third value which tells us the number of color channels that we have. In this case, we have the color channels. What we have is something that looks like a cube. There are 3 layers to this image. Each layer is stacked on top of the other. Each represents a color channel, red, green, and blue. We could print the shape of the label, but it has no shape because the label is essentially just like a scalar. And when we print label, we could see that it's a scalar and a rank 0 tensor. We'll see that because it says tf.tensor with the value of 0, but the shape is empty. So that's a rank 0 tensor. And we could see the data type is int64. Now we could go ahead and print the image. We know the image has 3 channels. It's 375 pixels high, 500 pixels wide. On the screen when we print the image, we're going to get a subset of the data. It's too much for us to see on the screen at once. But first thing that we see is those opening square brackets. So we have 3 opening square brackets. Then we have some values in there. After the first 2 square brackets, every set of square brackets opening and closing gives you pixel intensity values at a certain coordinate, and the coordinates are the height and the width. Now you have 3 values in there because you have 3 channels. So every value gives you the intensity of the red pixel, green, and blue. On the first line, we have 41 as the intensity of our red pixel, 22 as the intensity of our green, and 0 as our blue. Now it's important to note that with images, the pixel intensity values range from 0 to 255. If you notice from our last assignment, what we did was we normalized by dividing all of our values by 255. We'll get to that later. So essentially what you have here is the numerical representation of an image. In this case, it's an image with 3 color channels. And of course, we can look at all the numbers, but it's not going to make any difference to our eyes. Now we could go ahead and display this image that we're looking at. And we import matplotlib.pyplot as PLT, and we use a magic function, which is the percentage sign with matplotlib and inline. What this does is it lets matplotlib plot our image inside of the notebook instead of taking it outside. So we can make use of the imshow function and pass it our image, and we could see the output. We could see clearly 2 cuts asleep, or lying down, and we could see our image dimension. So we could see the height of the image, which is 375 pixels. We can also see the width of the image, which is 500. And if it were grayscale, you would have about 175,000 features. But it's a color image, so we need to multiply that by 3. You could start to imagine what the size of your input layer is going to look like. In the next video, we're going to look at an alternative approach to dealing with images in a neural network. It's called convolution.